Welcome to AP Daily for AP Chemistry. This is topic 1.3, Elemental Composition of Pure Substances. I'm Kristen Cacciatore from Charlestown High School in Boston, and I'm happy to be here with you. Today we're talking about pure substances. All pure substances have a fixed composition. So what that means is they have the same ratio of atoms of every element in every sample of the compound. So let's look at a couple of common examples. Sodium chloride or table salt has a 1-to-1 ratio of sodium to chlorine atoms for every sample of the compound, no matter where it's from. And water has a 2-to-1 ratio of hydrogen to oxygen atoms for every sample of the compound, no matter where it's from. This also means that there's a constant mass ratio for every sample of a compound. So going back to our two examples, sodium chloride is 39.34% sodium and 60.66% chlorine by mass, and water is 11.11% hydrogen and 88.89% oxygen by mass. So let's see where those numbers come from. We'll look at an example for a percent composition of another common substance, sucrose or white sugar, C12H22O11. You can see it sitting on the balance there, and a structural formula of 1 molecule of sucrose. So to find the percent composition of sucrose, first thing we would do is multiply the number of atoms by the atomic mass to find the mass per element. So taking carbon, there's 12 atoms of carbon from the subscript in the chemical formula. I find the atomic mass of carbon on my periodic table, 12.01 AMUs, and I multiply to find the total mass of carbon per molecule of sucrose. I can follow the same process for hydrogen and for oxygen. Once I do that, the next step is to add up those numbers to find the total formula mass for 1 molecule of sucrose. That's 342.3 atomic mass units. And then I can find the percent of each element by dividing the mass of that element by the total formula mass and multiplying by 100. This math gives me 42.1% carbon, and 6.49% hydrogen, and lastly 51.4% oxygen. So let's practice with this. I'd like you to stop your video here and try to find the percent composition by mass of N2O4, dinitrogen tetroxide, and I'll be back to go through the answer with you. Okay, so N2O4, let's find the percent composition. So first, we need to multiply the number of atoms of each element in this compound by the atomic mass. So for nitrogen, that gives us 28.02 atomic mass units. Oxygen, 4 atoms times 16 atomic mass units gives us 64. And then we're going to add them together to find the formula mass of N2O4, which is 92.02 atomic mass units. And then we're going to find the percent of each element by dividing its mass by the total mass to find the percent. And don't forget to multiply by 100, of course, for a unit of percent. So we get 30.45% nitrogen and 69.55% oxygen. So what do we do with percent composition? Well, the first thing to think about is, can two different substances have the same percent composition by mass? Yes, they can. So, for example, NO2 and N2O4 are two different compounds. They have totally different properties, but they have the same ratio of nitrogen to oxygen atoms, as you can see highlighted in yellow here, 1 to 2, 1 nitrogen for every 2 oxygen. And so that means that they have the same percent composition. So if different compounds have the same smallest whole number ratio of atoms, then they will have the same composition by mass. And so this leads us to an important concept, that of empirical formula. The lowest whole number of ratio of atoms of each element in a compound is called the empirical formula. And we distinguish that from the actual number of atoms of each element in 1 molecule of a compound is its chemical or sometimes molecular formula. And that becomes important when we start thinking about how we derive empirical formula from lab data. So here's a couple of examples. So in green, formaldehyde and glucose are two totally different compounds with different properties. Formaldehyde is CH2O. The molecular formula of glucose is C6H12O6. They have the same empirical formula, CH2O. And that's because if you divide the subscripts of glucose by 2, you get CH2O. I'm sorry, by 6. You divide them by 6, you get CH2O, which is the empirical formula of glucose. Formaldehyde, you can't reduce those subscripts any further, so the empirical formula is the molecular formula. And they have the same empirical formula and the same percent composition by mass. And then another example is nitrogen dioxide and dinitrogen tetroxide that we talked about earlier. They both have the empirical formula of NO2. And just to reiterate, if they have the same empirical formula as these pairs do, then they have the same percent composition by mass. All right, let's finish up with a little practice determining empirical formulas. So I'd like you to stop your video and try to find the empirical formula of H2O2, Na2SO4, and C2H4O2. Okay, so let's find the empirical formulas of these compounds. Well, H2O2, we can divide both of those subscripts by 2 and get a whole number, which is 1. So the empirical formula of H2O2 is HO. Na2SO4, well, sulfur in this compound has a subscript of 1. And so therefore we can't divide all of the subscripts by any whole number and get whole numbers. So that means that the empirical formula and the chemical formula are the same in this case. We can't reduce those subscripts any further. And lastly, C2H4O2, if we divide all of the subscripts by 2, we do get whole numbers. That's our lowest common factor, and it gives us CH2O for an empirical formula. So that's all for this video. In the next video, we'll talk about how to derive empirical formulas from lab data. Thank you.